So very good evening to yes, just a moment. So very good evening to all the participants. Welcome back to the fifth day of AICTE sponsored FDP and key technologies enabling 5G. Welcoming you all for the 10th session. So now I would like to request Mrs. S. Monica to introduce today's speaker, Rajkumar Tenua. So, ma'am, over to you.
I feel it's a great honor to introduce today's session resource person, Dr. R.K. Tenua, sir. Dr. R.K. Tenua is a young and dynamic faculty of engineering, well known for teaching MATLAB programming, certified from IIT Madras, India. He finished his BTech and MTech in electronics engineering and full-time Ministry of Education MOE funded PhD from Visvesvaraya National Institute of Technology, VNIT Nagpur in the domain of 6G wireless communications. Currently, he is associated with the Department of ECE at VNIT Nagpur. He has more than 70 years of teaching and research experience and is the recipient of the Best Teacher Award from Sharda Group of Institutions India in 2009 to 2010. He is a topper and gold medalist in various NPTEL courses from different IITs in India. He has assisted a number of research scholars from various IITs, NITs, and international universities like the University of Southern Queensland, Australia, Arizona State University, US, the University of British Columbia, the Korea Institute of Science and Technology Information of Korea, and many more. He is a member of IEEE, IETE, and ISTE. He has authored 26 research papers in various journals and conferences and one book titled A Review on Adaptive Filtering Algorithms, Practical Implementation Using MATLAB and CMS 320 C6713 processor with an international publisher from Germany. He has been invited for expert talks and training programs at various reputed national and international institutes and government organizations, including SLTC, Research University Sri Lanka, IIT Madras, Aerial Delivery Research and Development Establishment, Agra, and many more. Additionally, from 1st January 2025, Sir is joining as Senior Project Research Scientist at IIT Bombay. Congratulations, sir. Thank you, sir, for contributing your valuable time and sharing your thoughts and being a part of our FDP. Thank you so much, sir. Now I welcome and hand over this session to our resource person, Dr. R.K. Tenua, sir. Thank you all.
Thank you, ma'am, for a nice introduction. It's my pleasure to give talk in this program. So I'll just share my screen. So my screen is visible to all?
Yes, sir. Yes, sir.
Okay. So today talk is about the reconfigurable intelligent surfaces, RIS, and previously it was called as intelligent reflecting surfaces. Intelligent reflecting IRS and RIS, interchangeably these words are used, right? So this is very, we can say, emerging technology for future wireless communications. So today we are going to discuss about what are the emerging technologies, right? So I will discuss about that, and in that I will discuss about RIS and what is the architecture of RIS, what are the different applications in that we can use the RIS. Then what contributions we have done using RIS, what different models we have done, and we published the papers, all these things. So, and conclusions, and obviously there are some future research directions. So you can get idea in what direction you can work by using these technologies, right? So just we start with the introduction. So I hope You have seen this slide many times. Obviously, we are talking about the 5G technology, enabling technology. So 1G to 5G, these uh, we progress with these things. So in the 1G, obviously we were able to make the voice calls only. Then 2G message was there. So as the generation progressed, more number of applications are included, right? So in 5G, we can see we are talking about the ultra high speed videos, IoT devices. We want to connect more number of devices, right? So we can say there are three kind of the requirements as we are progressing towards the new generations. So one thing is the data speed. We are increasing the data speed. That should be high. Device density, because more number of devices are connecting. So we have to advance the technology that can support more number of devices. So that is one direction. Other direction is reduce the latency, because now we are introducing, or we are just expecting application, mission critical applications, autonomous vehicles, and some robots that are doing some operation, all these things. So these required very low latency, right? So this is the requirement in different generations, we can say. So obviously, the spectral efficiency also increases with each generation. So obviously, it is achieved with the help of different multiple access techniques. So in 1G, we used frequency division multiple access. Then in 2G, we shifted to the time division multiple access and code division multiple access. After that, wideband code division multiple access. And in 4G, we are using orthogonal frequency division multiple access, OFDMA, right? But in 5G and 6G, because we want to cater more number of devices, we want to connect more number of devices. So we are looking for some non-orthogonal multiple access techniques, right? So NOMA is also, lot of research is going on NOMA, how we can enhance the number of devices, number of users we can connect, right? So that is a potential technology. So non-orthogonal multiple access. So as per the Erection Mobility Report, November 2023, there will be more than 50 billion devices, right? 50 billion devices by the end of 2029. If you observe in these devices, just a minute. In these devices, the fixed phones, mobile phones, PC, laptops, all these things are about same, right? Its number is not increasing like that. But if we talk about the IoT, whether it is a wide range, short range, this number is increasing very large amount, right? So obviously we can say a lot of interest of the research is in towards the Internet of Things devices, IoT devices, right? So obviously this much number we have to, we can say, we have to fulfill this requirement. That number of devices we have to connect, right? So different kind of technology we require. So I'm just giving you some idea how you can get idea to do some research in some particular direction, right? So I am just giving you some interest here in what direction we are moving and what are the current trends. Okay. So far we listen about term Internet of Things. Now a new term is coming, Internet of Smart Things, right? Everything is getting smart. We are talking about the smart home, smart city, smart radio environment, right? Today we are going to discuss about it, smart radio environment, how it is getting smart. So obviously RIS is making the radio environment smart actually, right? So RIS comes in this particular scenario. Smart healthcare, smart grid, all these things, right? So that's why so many devices are need to be connected, right? So IoT, we all know, it defined as interconnection of machines and objects over the internet, right? So that have some computation capabilities, all these things. So in 6G, it is expected that a lot of significant rises there. We have seen election mobility report. So lot of numbers of devices are there. So we have to fulfill the requirement of the devices, how we are going to connect the devices. Okay. So what are the challenges in the IoT devices? because IoT devices, so obviously we want to connect that much number of devices, so we require some spectrum for that. So there's a scarcity of the available spectrum. We don't have that much spectrum, right? So there's a scarcity of spectrum. So that is the one challenge. Other is the limited battery life. Obviously, the battery life is limited, so we want to increase that life also, right? So these are the challenges. So the future systems that should be efficient in both spectrum and energy. In both terms, that should be efficient if you are working in such a kind of technology. So it will give some benefit to the society or the coming applications, right? So single technology is not sufficient to cater all these requirements. So there's a need to integrate multiple technologies, right? So nowadays, if you are working in the wireless communication area, you can see in a single paper, you are seeing multiple technology are integrated. So, so that is the reason, because one technology is getting some requirement, other technology getting some requirements, so like that. So multiple technologies are integrated. Okay. So what are the potential technologies? So I'm just giving you a little idea. After that, we will move towards the RIS. So first, I have discussed about the non-orthogonal multiple access, that is known as NOMA. So far in 4G or whatever the schemes are available that are orthogonal, right? Orthogonal. So suppose I say something is orthogonal in time. What is the meaning of it? If something is orthogonal in time, that means you are transmitting at different time instance, right? If something is orthogonal frequency, that means you are transmitting at different frequencies, all these things. So far, what is schemes we use that are orthogonal in nature, but non-orthogonal scheme. It is not orthogonal. So here I'm talking about basically power domain NOMA, right? So here two kind of we can say NOMA is of two kind. One is power domain, other is code domain. Code domain is somewhat similar to CDMA, like, right? But power domain, the users are segregated based on the power, right? So different power levels are allocated to the user. And based on that power, we are identifying the user, we are decoding the message of the user. Okay. So at the same time, we can transmit, and at all frequency, what a spectrum available, we can use those frequency, right? So all user can use all frequency all the time. So no constraint of time or frequency, all these things. So based on the power, we are just segregating the users, we can say, right? So obviously, if there are two users, suppose one user equivalent one that is near to base station, other is far to the base station, right? So more power is given to user 2, right? And less power is allocated to the user 1, which is near to the base station. So obviously it is base near to the base station. So we can say its channel is a strong channel it has. So SINR will be high at this point, but here it is a little far. So channel gain is poor. So more power is required, right? So whatever the user which is away, it can decode own signal, whatever the signals available for other user that are considered the interference or noise. So signal to noise ratio, like that. So it can decode directly own signal, but the user which are near to the base station, they decode first other users signal, then decode own signals, like that. So it's a basic principle for the NOMA. So the main point is that by allocating different power levels, we are able to differentiate different users. We are able to serve different users. So obviously, we are increasing the spectral efficiency here, right? So that is the objective. Because in orthogonal, obviously, we are dividing resources. Frequency, you are dividing to different users. So again, obviously, how many slots you have, how many bands, frequency bands you have, that much number of users you can support it. But here, we are not doing like that. Okay. So you can further explore it. So I'm just giving a basic idea, right? Other things, so it gives it gives an opportunity to improve the spectral efficiency, right? We are using spectrum efficiency efficiently, so more number of devices or users can be connected. Other technology is the cognitive radio. So cognitive radio, basically here, two networks basically exist. First is primary network, that is licensed one. Other is secondary network. Okay, secondary network. So secondary network is unlicensed. So now there are three different modes how we are basically transmitting the data. The secondary network, how it is transmitting the data. Primary is the licensed one, right? So we have to take care about they should not interfere. You are secondary user, you are unlicensed, so you cannot interfere the primary users. So their quality of service should not impact. You have to take care about that. So by considering that, you can build a network as a secondary network, and you can perform the communication task. So in cognitive radio, there are three modes of operation. One is overlay, underlay, and interweave, right? So in overlay mode, the secondary network, whenever primary network is transmitting, so here this is the primary network, right? Primary network users, and these are the secondary user, yellow one, right? So when primary users are transmitting, at that time, secondary users support the primary users, right? Right. Either they are using like relay, or they are just supporting the transmission for that. They are not transmitting own signal. They are transmitting primary users. When there is a slot empty, primary user is not transmitting. In that case, secondary user transmit their own data. So in this way, this is the overlay. So whenever slot is available, at that time they are transmitting own data, and otherwise they are supporting the primary network. Other is underlay network. In underlay network, secondary users transmit always, but within certain threshold. The condition is that the primary user service should not interfere. Within the limit, they can transmit all the time. So there is certain threshold. The power, transmit power for the secondary user, that should be within the limit. Okay, so it limit the data rate, we can say, right? So now it depends again on the application, what application you are using. So, but now these are the unlicensed user, and these are the licensed one, primary user, secondary user. So obviously you are increasing more number of devices, right? You are increasing number of users. You are supporting more number of users. No additional spectrum allocation required. Okay, and other is interview. So in interview mode, they continuously sense the channel when channel is available, secondary users. So when channel is available, then they transmit the data. When primary is transmitting, they are sitting quiet. They are sensing continuously. When their channel is idle, right? Whatever, at what frequency channel is available, so they will simply transmit at that frequency, right? So they are observing all frequency slots like that. Okay, so these are different modes for the cognitive radio. So by considering different modes, you can make different works. You can do the simulation. You can analyze for different scenario, right? Because different we can say different modes can be used in different applications. So based on that, you can do some work, right? Next technology is ambient backscatter communication. It's also emerging technology. Backscatter communication. So it's a part of backscatter communication. So backscatter communication is not new, but if we talk about the ambient, it's something new, right? So in backscatter, we are talking about the toll collection. So there's a fast tag. So fast tag signal is going there and it is reflecting back. So that is a backscatter device. So obviously it's batteryless. It is just reflecting the signal. You are getting the information, whatever information there. So that is the backscatter, simplest example for that, right? So in ambient backscatter communication, what we want, as in the starting I discussed, for the IoT devices, we want to make the devices, we want to increase battery life, or even people are working in the direction to make the IoT devices battery free, because that number of devices are going to be connected in future. So keeping that much batteries, that is again a problem, right? That will create one kind of waste, all these things. So that is a problem. So, and again, recharging those batteries, replacing those batteries, a very difficult task. So researchers are working in the direction how the battery life can be increased, or we can make the battery-free devices, right? So ambient backscatter communication, this ambient backscatter communication technology, AMBC, here the signal is coming, ambient signal is coming, right? And here is the backscatter device. So it's simply getting the signal and reflecting. It is modulating own information, right? So it is again passive device, we can say. It's a passive device. It's a signal is coming and it is reflecting, as I discussed about the tag, fast tag, but we are talking about the IoT device also that should be able to transmit their data in the same similar manner, right? So we are modulating that signal by putting different impedances. We can say we are changing that impedance, and based on that it is transmitting. So here it's simply two labels. Here we can say it's just transmitting 0 and 1, right? And we can detect this at the receiver side by using the envelope averager, threshold calculator, all these things. So you can detect that, right? So it's possible. So the objective is that we are using the ambient signals, because whenever you are transmitting, for the transmitting, you have to generate RF signals. So for generating RF signal, some power is required, right? That is the most important part for the, we can say, that requirement of power is mainly for the RF generation. So that we are avoiding, right? We are saving power in that sense. So these, we can say, this technology is mainly useful for the IoT devices. When IoT devices, because they are power, we can say we have to save power in any sense. So by using the ambient signals, we can reduce the power. Okay. Then we come to the reconfigurable intelligence services. That is the today topic, and what are the different applications, how we can use it. So it support all these technologies, right? As I discussed, we are integrating the technology. So I just getting you aware with the different technologies. So this RIS is mainly, we can say, making the environment some intelligent, right? Radio environment, because you are just sending the signal is going to any direction, and at the receiver, signal is coming from different directions. So obviously its strength is not that much, right? So by using RIS, we can direct the signal in some particular direction, and we can enhance the signal strength at the receiver. So that is the main objective. So in normal reflector, simply question comes in the mind: what is the difference between the regular reflector, like a glass, you have mirror, right? Mirror is there, and reconfigurable intelligence surface. So what is the difference between these two? And we all know that by using mirror, suppose there is some dark room, right? And you want to bring some light in that. So by putting mirror in such a way, so you can redirect the light waves in that particular room, so you can get light. We all have idea about it. So same concept is tried to utilize in these reconfigurable intelligence surface, RIS. So how we can redirect that electromagnetic wave, right? What wave is coming, how we can redirect it. So in conventional this mirror reflector, what happens? The angle of incidence should be equal to the angle of reflection. So that is the simple rule. Okay. But in this intelligent one, that makes it intelligent basically, because we are using intelligent surface. So intelligent surface means the angle of reflection, angle of incidence, and angle of reflection both are not same, right? You are receiving signal at θ1 angle, and you can transmit at some different angle θ2, right? So with the help of that, because in what direction the user is there, the objective is that we want to redirect the signal towards the user, right? Where is the user? In that direction, we want to redirect the signal. So where is that phase? How we are managing that phase? This obviously the θ1 should be equal to θ2, but these two are different because θ1, θ2 we are considering. So how this phase difference is basically nullify, or it is managed. So these are the elements. It has elements, right? So these elements introduce that phase, right? Phase delay, some additional phase delay we can say. So how much we are giving that phase, that depends. right? So that gives this, we can say, freedom. So in what direction we can redirect the signal. So we have to set the phase of these elements, whatever the elements we have. So we have to set the phase of these elements, and we can set the amplitude of these elements also, right? So suppose some signal is xm is the incident signal, right? And ym is the reflected signal. So simply the reflected signal is given as it is the it is multiplied with the complex reflection coefficient, right? So this is the complex reflection coefficient, which has two component. One is corresponding to the amplitude, then chi m, which is represented chi m, and e to the power j theta m. Here this theta is corresponding to the phase, right? So this chi m is between 0 to 1. If it is 1, that means whatever signal is incident, it is reflected, right? There is no loss. It's a passive device basically. So whatever signal we are considering, it is just getting. Sometime if it is attenuating, if it is introducing some loss, so obviously its value will be less than 1. In some cases, its value is greater than 1 also, right? Because a lot of research is going in this direction. So these values are also changed. In some cases, you may get it more than 1. So in more than 1, the type of RIS will change. Currently, what RIS I am showing you, this is passive RIS. It's a passive. Whatever signal is coming, it is reflecting, it is not doing anything, right? Only some phase, we can say some phase introduced here. And accordingly, it is just transmitting it. But when it is more than 1, that means it is amplifying the signal also. So in that case, it becomes active RIS, right? Active RIS. So that is also useful. But if you are using RIS in some applications where energy efficiency is important, you are talking about the energy efficiency. In that case, we want to reduce the energy. But if you are using here active RIS, obviously you have to give power to these elements. You have to provide power for the amplification. So again, like RF chain. So all these elements you can consider like antennas. Yeah, different antennas. So by using different antennas, we can form a beam. So beam forming is done with the help of that, right? So when different antennas are radiating, so there's a we can say constructive interference or destructive, that depends. So based on that, we get some beam. Okay. So other is a theta, which is from 0 to 2 pi. So sometimes people get confused. 0 to 2 pi, that means it will transmit signal, or it will redirect this to 360 degree. Not like that. This is about the phase of the signal. So signal phase is 0 to 360 degree, right? So that is the phase. So it will introduce that phase because it's a phase shift. So it will introduce phase shifts. Accordingly, the signal will be interfere whether they are constructively or destructively. That depends. So that is about that, right? Beam steering is different thing. Beam steering angle is a different thing, right? So here we consider m number of RIS reflecting elements. Okay. So in this manner, we can form different beams in which direction user is there. So that beams can be formed. Okay. So for that, we use the RIS controller or IRS or RIS, whatever we say, right? So it's a control circuit board is here, copper backplane is there, and here we have reflecting elements that are known as meta atoms, right? Meta atoms. So here we have either a pin diode or varactor diode. All these things are there. Okay. So by giving different biasing voltage, we can introduce different phase delays. Okay. So here we are in case of varactor, in case of this pin diode, we are just making it on off. So we can say we are just introducing 0 or pi degree phase shift. Okay, like that. So if we talk about the applications, suppose there is some user which is behind some building. Okay, so these users are known as a dead zone user. They are not getting directly signal from the base station, so they are getting very weak signal. So in that scenario, you can put the RIS at the top of some building. So the signal will come through this, right? After reflection, you are getting the signal. So it will get better signal strength. So you are able to serve these dead zone users with the help of this RIS, right? Other application in security, for physical layer security, Suppose some eavesdropper is here, right? And these are the legitimate users. So these are the, we can say, intended users. We want to transmit data to these users. But this is an undesired user that is just stealing the information. So by just setting the phases of this RIS, in this region is the nearby region, right? In this nearby region, we can create such kind of phase shifts. Whatever signal is coming, that is canceling this direct path. We are getting one signal from direct path. We are getting from the reflected path. So we can set the phase in such a way, whatever signal will come here, that will distract actually, right? So destructive interference as I call it. So here the signal strength will be very less. So it will not able to get that signal, right? And here these user will get the signal whatever they are getting from directly. So the objective is just to cancel out this signal. So this is another application where physical layer security can be done. Other is if some user at the cell edge. So obviously at cell edge, signal strength is less. Okay. So if signal strength is less, in that case, we can coordinate with the different base stations. So it's a coordinated multi-point scenario we can see. So here, one signal is coming from this direction, other is coming from this direction, and it is getting a stronger signal, right? So whenever it is cell edge, signal strength less. So we are coordinating with the two different stations, right? So we are getting signal from one path is here, but we are getting from reflected one, also reflected one. So it is coordinating, and the signal strength is getting. So these are different scenario in which you can make the model of such kind, right? And other is massive device to device communication. When a device want to communicate, in that case, big size RIS can be put, right? So it is just assisting all these devices. So they are just reflecting, and they are getting the signal back from here. So in different applications we can use. Other application is simultaneously power and information transfer. That is SWIFT, it is called, simultaneously wireless information and power transfer. That is also one concept we can say. So here the power is transmitted for these devices which are required basically power, and these are some devices which require information. So for that, information is also transmitted, right? So by using these multiple RIS, we can serve these devices. Okay, because simply we are just redirecting the signal. We put different RIS, so they are reflecting back the power, and obviously it is getting towards the devices, right? So this is other application we can say. So I discussed about it also, active and passive RIS. So in passive RIS, it is introducing a phase shift. So passive, there is no amplifier. So whatever signal you are getting, so obviously the signal strength will be limited. Signal strength is not that much, but if you want to get a higher strength, in that case, you can switch to the active RIS. So in that case, obviously it is amplifying, right? So whatever input it is getting, the output is more strong. Okay. Here, whatever input you are getting the same output. So it is not amplified. So in case of passive, so it depends basically what kind of application is there, because when you are going towards the active, lot of complexity involved, right? Because amplifier is there. So power requirement is there for this particular section. For the heating, there may be some arrangement, okay? And lot of circuit complexity also include for this one. So it depends on the application again. If that application requirement is like that, so you can do this. But suppose you are working in some power, in some application where power is the main concern, you cannot give the more power like that. So in that case, we go for the passive, right? And apart from these two configuration, third configuration also there. That is the combination of these two, the hybrid RIS. There passive RIS there, and some active elements are there. All elements are not active. Few elements are make active. Reason is that because what happens in passive RIS, when because whenever you want to communicate, first of all you have to estimate the channel. You have to done the channel estimation. In passive RIS, problem is that when you are transmitting some signal and it is getting reflected, or you cannot estimate the channel from base station to RIS or RIS to user. Individually, you cannot estimate. It is estimated combinedly. You are transmitting some signal and it is coming back to the user. So combined channel we estimate in case of passive RIS, right? So there we can say not a proper channel estimation is there. But when we have some active element, in that case, this individual channel estimation is also possible. So for proper, because all thing works based on the channel estimation. If channel estimation is good, then you can do the proper beam forming, right? Otherwise, beam forming will not work like that. If channel is not properly estimated, so beam forming concept will fail. Okay, so how much better you are estimating the channel? According to that, your we can say what concept you implemented that will work. So channel estimation is an important thing. So for that purpose, some people are planning, we put some active elements and we will estimate the channel and things will work properly. So that kind of configurations are also working, right? Nowadays, you can see in the literature. So I just try to put a different kind of things because whatever time we have. So in that time, you can get more and more information what currently going in the research, what people are doing, right? Because RIS introduced I think in 1819, at that time it was going on. So I started research in 2021 I started research. So at that time it was again new topic, and now a lot of people are working in this direction. So every paper you will see RIS is there, RIS there. So now what contributions are there that we have done? So this is the first contribution where we done the joint beam forming design for this RIS. So because I use these technologies, ambient backscatter, NOMA, all these things, right? So that's why I just introduced about all these technologies, how you can make the models, how you can go for the simulation, all these things, right? So this work is published in December 2023, right? So here we use one base station, and this is the RIS, and again dead zone user. So we use the application scenario from whatever I have shown you. So I pick simply from there, and I just start thoughting, yes, what we can do here. So whenever you are doing some beam forming from base station to RIS, this is known as active beam forming, right? This is active beam forming. Base station is involved, so it is transmission power. So it's active beam forming. And from RIS to users, it is known as passive beam forming whenever you are using passive RIS, right? So we done active beam forming and passive beam forming to serve these users, right? So here mainly this theta, we consider all the elements of this RIS, we put in a diagonal matrix that is represented by this big theta. In most of the paper you will see by this big theta it is represented, right? So it's a diagonal matrix, so it's a square, m by m. M is the number of elements on the RIS, okay? So on the other thing are same. Here I have considered xi m is equal to 1. That means there is no amplification, right? Simply whatever signal we are putting, that is just transmitted, right? And NBS is the number of base station antenna, okay? So these are the simulation parameter that we use for this. So I have not gone to the mathematics for this particular because that is a different thing. Mainly you have to understand, yes, when we are using the RIS, we are getting some advantage or not, right? So that is the objective. So here, this green line basically showing the RIS NOMA random when phases are random. So obviously here multiple phases are there, right? So what phase we should set that will make a beam towards that particular user? So what phase should be there? So uh, because whatever signal is going, it is reaching to each element, right? It is reaching to each element, and it will make beam for user 1, user 2, for different users. So what should be the phase of that particular element? So it cannot be directly, analytically, you cannot find that expression. Okay, this is the expression and you can find analytically. So that is not possible. So in such papers or research work, you will see we are doing the optimization. We want to optimize the phases. What will be the optimum phases? So by using that, we are getting the proper beam to the desired user, and we are getting some maximum, whether you are maximizing the capacity, or you are maximizing the energy efficiency, whatever you are maximizing, right? So that you can achieve by optimizing. So optimization is involved here. Okay. So here in this condition, phases are not optimized. Only the condition we put one RAS and we observe what is the impact. So in this case, here, because I have not compared with the without no RAS, I have not compared because the objective was that here I was comparing these two schemes. If I put one more scheme that is without RAS, that will go more down. In that case, I will not be able to visualize this difference, right? So that due to that, I have not put here that without RAS scheme. But in next work, you can see when we are not using the RAS, and we are using RAS without phase optimization, that have better performance, right? If you put the RAS, you do not optimize the phase, still you will get some better performance, not that much. But once you optimize the phase, there will be huge difference in the performance. So here it is the unoptimized phase and it is optimized phase, right? So that's why different optimized techniques are also used. What kind of optimization you are using, right? So that again, you have done some, same kind of scenery you have considered, but you are using different optimization technique and you are getting better results. So that is again contribution from your side, right? So in this case, we got 31% to 38.76% better sum rate, right? So here we consider the sum rate. And when you increase the number of RIS element, again, this sum rate increases, right? Sum rate is simply we are adding the data rate of each user, right? That is the sum rate in a bits per second per hertz. So again, when you are using the number of RIS element, this is increasing sum rate. Okay. So this is starting basic for the dead gen users. This is the most important work that I actually liked, right? And it has all the concept what I have shown you. Okay. So this is sum rate maximization for RAS assisted, NOMA enabled, underlay, AMBCCR. So in this, I am using all four technologies, and I am using cognitive radio underlay mode, right? Underlay. So I have discussed all three modes, right? What are the three modes? So I am using underlay mode. So this is the system model, right? So in this system model, what we are using, we created one secondary network. This is the cognitive radio network, right? We created one secondary network. Here we have n number of backscatter devices. Okay, n number of backscatter devices we have. These devices want to send their data to a common point, that is backscatter receiver. Okay, so again, this link is not that much strong. So we put here one RIS, and because these are the backscatter device, so this link is weak, right? This link is weak, so we are not getting that much of whatever the requirement we have, we are not getting fulfill these requirements. So we used here one RIS. Okay, so through RIS, we are getting direct signal, and through RIS signal. So here we are getting a composite signal for each backscatter device. Okay, and this is the primary network. So this primary transmitter is transmitting to this primary receiver. So it is using these signals. Whatever signals we are getting, these backscatter devices are receiving signals from the ambient, from the mobile tower or Wi-Fi point anywhere. So it is getting signals and modulating own message over that signal and transmitting. And that is recorded here. Okay. So RF is not generated here. So they are saving the energy. Okay. Here, condition is that when they are transmitting, all are transmitting, obviously some interference will come here. Primary receiver will receive some interference from all the devices. Even from the RIS, it will receive the interference. So that interference should be within the limit. That should not compromise the quality of service for this primary receiver, because this is a licensed one. And secondary users are unlicensed, right? So, and we are using in the underlay mode. So all the time we will transmit. All the time we will transmit. But the condition is that you have to transmit within the threshold limit. Interference threshold is there. You have to limit with that. If a primary receiver say, yes, you can transmit your threshold is higher, no problem. you can transmit with more power, it's fine. So we saw the impact of that threshold also, right? So again, it becomes a optimization problem. You have to optimize the reflection coefficient of these backscatter devices in such a way that the power received at the PR should be within the interfering power, what it is receiving, that should be within the limit. And you have to make the beam forming again. Whatever the signal is coming from RIS, you are making the beam forming here, right? So that signal is reaching here. So that you are doing. Okay. So you have to optimize the power reflection coefficients for this BDs, right? And RIS phases. So that is the objective. Okay. So that is done in this work basically. So here we consider the signal, and this is the interfering signal that is coming from all the users, right? So that we have to minimize. Okay. So first we find the SINR expression, we find that, and we write the expression for the data rate for each backscatter device. So for nth backscatter device, written is like this. So it's a data rate, and we optimize this. So this is the maximization problem, right? So we want to maximize the sum rate of all the backscatter devices at the backscatter receiver. Under the optimization variable theta, big theta, and rho n is the reflection coefficient for nth backscatter device. Okay, so here one condition is the minimum data rate requirement we have to preserve. Whatever minimum data rate requirement, that should be met. So in the optimization problem, one is you have to make an objective. So objective is we want to maximize the sum rate. Other thing is you have to put some constraint. Obviously, you are maximizing, but there are some condition also. So you have to fulfill those conditions that are the constraints. So we are putting these constraint. Minimum rate should be whatever rate we are getting, that should be greater than minimum for each user. Nth user it is given. So if here we have 5 users, then this constraint will be repeated 5 times. We can say these are 5 for each user. Again, because in NOMA we use successive interference cancellation. So for that, this is the condition, the channel gain condition. This is for the threshold for the, we can say, controlling the interference power. So the sum of all the power, right? That should be less than the threshold power. So this is controlling for that. This is for the phase, whatever phase it is picking, that should be from 0 to 2 pi phase shift. And this is the reflection coefficient value from 0 to 1. So these values we have to put. After that, we have to look whether this problem is convex, non-convex, what kind of problem is it is, right? So we have to identify that. Based on that, we solve this problem, right? So here I used alternative optimization. So using alternative optimization, we break this problem into the different sub-problems, phase shift optimization and power reflection coefficient optimization, and we solve the problem, right? If you are interested, you can refer our papers, which are available, because all these things are published. So you can refer. So I have not included everything is here, right? So there's a simulation parameter, and this is the convergence graph that show how fast our algorithm converges, right? So within 4 iterations, it is converging. And this is the result here we can see. So so here we compare with the conventional scheme, orthogonal multiple axis. So now here we compare the orthogonal and non-orthogonal schemes also. We compare RIS and without RIS also. When we are using RIS and we are not using the RIS, how much improvement we are getting, right? So here it is compared with the NOMA without RIS. So when we are using NOMA scheme, right, and using the RIS, in that case, we are getting 25% advantage in that, right? In case of OMA, when you compare OMA, orthogonal multiple axis, without RIS, in that case, we are getting 57.78% better performance, right, in terms of sum rate. Okay. And other are for the NOMA random when you are using NOMA random. So NOMA random means it uses RIS, but phase are not optimized. So in this case, again, you can see this is NOMA without RIS, and this is NOMA with RIS, but without phase optimization. So it has some better performance, right? Some better, but not that much. Once you optimize the phase, the performance increases, right? So that way optimization is very important. The phases should be optimized for that particular scenario, right? And it is compared with the without RIS again. So when here you can check when we are increasing the number of RIS elements. So when we are increasing number of RIS element, performance getting much better, right? So here it is 60.63% when RIS elements are 90, when we increase from 40, right? 40, 50, then increase to 90 around, then we are getting that much improvement. When we compare with the OMA, that is conventionally used, right? When we compare with that, we are getting 141% high, right, in that. So NOMA is, we can say, a potential technology. And when you are combining this with the RIS, it gives a much better performance, okay? So this is just represented how the threshold is controlling this sum rate. So when threshold is suppose minus 120 dBm we consider, that means threshold is less. It means receiver is more sensitive. If you put little interference, it will not tolerate. So in that case, its sum rate will be limited. When you are making it minus 40, it will bear interference up to minus 40 dBm. That means it can bear more interference, so we can transmit with more powers. Backscatter devices can transmit with more power, so they are getting better sum rate. But again, they get saturated because when you increase it to this level, backscatter devices some limited power. Whatever they are getting the signal, now they are transmitted with full power. So this sum rate again saturated because now further it cannot increase. If you increase the number of RIS element or if you increase the transmit power, again obviously this will be shifted. So these two cases are also shown here. Okay. So this is another case. Now another is one more thing I am discussing, that is star RIS. I discuss about the passive RIS, active RIS, hybrid RIS. One more thing I am discussing, that is star RIS, simultaneously transmitting and reflecting, right? It is simultaneously transmitting and reflecting. So in normal RIS, what is the problem? Whatever RIS we have used, in that RIS, there is one limitation. Whatever the transmitter and receiver, you have to put both in front of the RIS, right? In front of the RIS, you have to put. If something like transmitter, receiver, anything is backside of the RIS, it cannot help. Normal RIS, conventional RIS, what we have discussed so far. So the requirement of star RIS can serve in both the directions, right? It can reflect the signal and it can transmit the signal. So here it can operate in 3 modes. So here this is the energy splitting. So whatever signal is coming, this is the incident signal shown by the red. So this signal is coming. So it is reflecting some signal, some part of the signal, and transmitting some part of the signal. So each element is working like this. Okay. So transmit and reflection mode, they are working. So some portion of that power, whatever power it is getting, that is reflected, right? So energy basically. So that energy is reflected and transmitted. Now again, it depends on the application. What is the main requirement? So it is you have some devices in front side and other some back side. So you can sub both the diagrams, right? Other is mode switching. In mode switching, some of the elements are reflecting, some are transmitting. Okay, transmitting and reflecting. So here number of element will decrease. So again, if they will decrease, the rate may decrease for that. Okay, so again, it depends on the application. What is the application? Here, time switching. In this, at different times, the complete RIS, we can say, one time it is reflecting and other time it is transmitting. But in that case, all elements you can use. Okay. So again, it depends on the application. What application, if your data rate requirement is high, in that case, you require more number of elements. So once you fix the RIS, so you cannot increase the number of elements. So in that case, if you operate in this mode, more number of elements you may have. Okay. So sometimes we are using this, sometimes people are using this. Suppose, yes, we want to put one RAS, and because here time is distributing, so obviously it will impact the performance. Okay. And here number of elements are decreasing. So every mode have their own pros and cons, we can say. Okay. So we have explored basically this time switching mode because we are using the backscatter devices, right? And so just to give more strength signal, we require more number of RIS elements. So we use this time switching. right? So in this case, what model I have used previously in that the similar kind of things we can say we put NT number of devices that are transmitting. Their signal are transmitted basically here, and these are in front of this. If this side is front and this is back, what do you think as you consider, right? So this is the reflected signal. So these are reflection R devices we consider. The same thing we have used, right? So in this way, we are just increasing the full space coverage, spherical coverage. In any direction, any devices there, you can serve that. In conventionally, you can serve only 180-degree, we can say. Now your coverage is increased to 360-degree, like that. Okay. So here the things are similar. Only one additional thing is increased: transmission and reflection time. So that we have to optimize, because some device requirement may be less, like that. So you can optimize that time also. Okay, reflection and transmission time not necessary 50% are divided. You can make it 40-60 or in that way. Okay, so that can be also optimized. So that kind of problem also done. So in optimization problem, one more constraint will include it. You have to optimize the transmission and reflection time. So we are optimizing the phases, we are optimizing the reflection coefficient, we are optimizing the transmission reflection time, right? So here again, we simulated. So again, this shows the speed of the convergence, how fast it is converging. And here again, we got better performance for those cases, right? So these are the different cases. So again, here it is showing. So here we consider basically 6 number of users, right? So that's why whatever performance you are getting, there's difference because number of users are 6, right? That's why. Okay, so I think, yeah. So we introduced about the different technologies. I think for 1 hour, I think I included so many things, right? So we discussed about the different emerging technologies. So I think, I don't know how many are aware about all these technologies, right? And so I just try to put different names. If today you pick some names itself, and if you start searching about those names, definitely in some days, you will be able to do the research on that. In 2021, I just heard this name from Taiwan, this RIS. So when first time I saw this, so I thought, oh, it's very difficult. I will not go inside this. It's a big mathematics is there, right? So I feared a lot. But later I thought I just started over it. When I look everywhere, I am seeing every research people, everybody is going towards this direction. So a lot of work is going there. And I don't know what time I switched in this direction and I completed my PhD in this direction, right? So once you come across some word, that word may change your direction totally, right? So here we discuss about the different technologies, different types of the RIS, right? And we discuss about the different networks that we proposed in those networks, and we saw the performance, how much performance we are getting in each case, right? So, so these are the basically we can say we try to reduce the power consumption. We have not done specific analysis for the energy. We have done mainly for the spectral efficiency. So we just try to improve that. Okay. And by using RIS, we just try to mitigate the problem of weak backscatter signal, because in backscatter device, signals are weak. So we want to improve that, right? And in different scenario, we just show you how much percentage benefit you are getting. When you are increasing number of RIS element, again, the performance become more better, right? And we address the coverage limitation problem also. Conventional RIS has the coverage limitations. So by using the star RIS, you can cover the complete area, full spherical coverage, right? So obviously, whatever research we have done, hopefully this will be useful for you people, or whatever the people they are doing research. So that may be useful for that, right? So what are the future research directions that is important? So because if user behavior is dynamic, right? If a user is moving, in that case, how you can change the RAS configuration. So dynamic RAF configurations can be used. So machine learning, all these things are coming into picture in that case, right? Because in that case, some we can say advanced machines we are using with the good uh, configurations. We are using machine learning, all these things, right? So different kind of machine learning techniques are going to use. So dynamic arrays configurations, for that we can use machine learning, all these things. And in these models, we use the underlay mode for the cognitive radio networks. You can explore for the overlay, interweave mode, all these, right? And because whenever you are working with some new concept, we start with some assumptions, right? And as the time passes, as the time goes and research advanced, we just try to relax those assumptions. So once the assumption relax, that means you are moving towards the practicality, right? So in this work, we consider some assumptions, obviously, in starting, but further work can be done by considering imperfect channel state information. In this, we consider perfect channel state information. You can consider imperfect CSI, right? And hardware impairment also can be considered. So that will result in different works, right? And here we just done the spectrum analysis, spectrum efficiency. You can do the joint optimization for the spectral and energy efficiency. All these things can be done, right? And currently, we just started without, in one work, we consider energy harvesting constraint, energy harvesting we have done. In other work, we not done energy harvesting. So that is also possible. You can include energy harvesting. So that make the things, we can say IoT devices, as I discussed, to make it battery free, right? All these things. So a lot of work is available in this direction. So a lot of ideas are there, right? So I hope you got some idea about this, right? So for this work, I got received one award for this, right? All this contribution, right? Recently. So all the work, whatever I have shown you, that is recent in 2024 itself, right? So everything you are just watching latest thing, right? So these are the references. So I think it is sufficient from my side. So if you have any query, it's welcome.
Thank you, sir. Thank you for such a wonderful session, enlightening us with the emerging technology, reconfigurable intelligence services. Sir, actually, coming to the hardware, for example, what size actually we need to consider, sir? Like, what should be the sizes of these arrays?
Size for one element you are saying, or for complete RAS?
One element, or for example, in that we are having some 4x4 or 8x8 like that.
So it's actually, frankly speaking, my work is mainly for the signaling part, right? But I just discussed
Okay.
with some people. So that is around, it actually depends on the frequency of operation also, right? Because when you are working on the higher frequency, obviously size will be reduced, right? If you are increase antenna size like that, because we are talking about the antennas. So that is around 1 centimeter by 1 centimeter kind of thing you can consider, right? Around
Okay.
that. So it depends on the frequency also. So that is
Coming to the
the
coverage
implementation
area,
part. Yeah.
coming to the coverage area, sir, it will cover up to what area?
Coverage basically how much power you are giving. It depends on that.
No.
Simply, it is redirecting some signal.
Okay, with the help of AICTE, we can boost the
So we
signal.
can in the future actually large intelligent reflecting surfaces are going to put, like on window it is put it, on some wall it is put it. So it is simply reflecting the signals. For the indoor it is wonderful. In indoor, suppose in indoor scenario in your house coverage is not good. So simply you put the RIS and coverage will improve automatically. Because signal are reflecting from different directions, na? So it will reflect in direction. So it not that much optimization required for indoor scenario, but outdoor it is a lot of optimization. All these things are required. So, but coverage again, it is extending the coverage, because when directly signal is receiving, signal strength is less. But when additional path is there, so signal strength is improved. Now, if you are moving away, the signal strength is improved now, so it can go little away also. So in this way, we can say we are extending the coverage area also. right?
Yes, sir.
Like that.
As a
Yes.
users are dynamically moving, it is little bit complicated to allot the power to users depending on their position
Yes, yes, that's why
or
we are
panel
saying for
condition.
machine learning, all these. So at that time, cloud computing, all these things come into the picture, or a high-end processor required, all these things. So yes, in that case, because optimization also itself, when we are optimizing, time is very important because channel change very fast, na? So all these
Yes,
things should be
yes, yes,
done within milliseconds. So
yes,
then,
yes.
yeah, so research is going on in that directions, right? And the devices are also getting more, we can say, the devices what we are getting that are getting more efficient, computationally efficient, right? So in the future, that's why it is not the current thing. It is a topic of, we can say, 6G, right?
Yes,
Beyond
yes, yes.
5G and 6G.
Sir,
So lot of research is going in this direction. Yeah.
sir, one more last question, sir. In that star IS, how can we switch the elements, sir, actually for performing different functions?
Actually, we are just in what actually we have three modes, na? So you have to
Yes, yes.
yeah. So different modes you have to use. So obviously, element, that kind of element you have to use. That mode, na,
Can
when
you
you are
switching? Can you
one star IS will not work in all three modes, right? So
so for
during the
example,
time of the fabrication or when you are making it, at that time you have to decide in what mode you are going to operate it. Okay.
because it is dynamically very na, sir, in real time. So
So obviously we are just switching on, switching off like that.
okay,
What portion we are switching off and switching on.
okay, sir.
So
Thank
turn by turn, no? It is a time
you.
division. We again say we are using the time division duplexing kind of thing. So we are just making off some portion is working. So whatever off they are used for the transmission, other for reflection, like
Okay.
that. Hmm.
So with any algorithm, we can do that. Like,
Yeah, yeah, huh, obviously.
okay. Thank you, sir. Participants, please ask
Uh,
questions.
Sir, may I ask question?
Yes, sir. Yes, you can.
Sir, I'm the one of the participant from the Amravati, nearby Nagpur.
Yes.
Hello. Sir, I'm the means beginner for the research work. I'm trying to find out the some research gap in radio resource allocation mechanism. So what you suggest topic?
Yes,
Radio.
actually, my talk, if you attended this
I
from the
want to.
starting, so I think
This topic
I was
is
just giving you the direction itself, right?
yes.
So whatever latest we have done and what are the possibilities. So in that direction you can do. Again, I discuss about the different technologies, right? So it was
Mhm.
not only the RIS, I discuss emerging technologies, in fact. So now it's your choice in what direction you want to work. Resource allocation, they are different kind of resources. When we are talking about the RIS, so in RIS, we optimize the phases. So that is again comes under the resource allocation. Hmm? So yeah, so what technology basically you are considering? We done that we use the backscatter devices. So we are optimizing those reflection coefficients. So again, that is a resource for that. So all these things comes under the resource allocation. So whatever resource we have, power, NOMA we have used. So we allocate the power in first scenario, we use the beam forming vectors. So there we allocate the power, right? So that is again resource. So it depends first what technology you are going to work in that, what resources are there. Obviously, you have to optimize or allocate those resources like that.
Okay, sir. Thank you, sir.
Hmm. Okay. Any other query?
Any other questions from participants?
I think so. There is no query. So or they can reach me. I have shared my email ID
Yes,
also. So if
yes, sir. Yes.
any doubt, yes.
Sure, sir. Sure, sir. Thank you, sir. Thank you so much for such a wonderful sir. Really, sir. So really enlightened us what we need to do. So in future directions also you have shown us.
Yes.
So what is the scope for doing research? So because most of us are coming from faculty community.
Yeah,
So
yeah.
really, sir, really very gratitude to you, sir. Sir. Thank
Thank
you,
you,
sir.
sir.
Thank you so much, sir.
Okay, sir. It's my great pleasure, sir.
Sir.
Thank you, sir.
Thank you.
Madhu, sir.
Sir, sir.
Sir, is there any further session?
No, sir. Today, actually, yesterday only
Yes.
we told, sir, morning one session over, sir.
Morning I was attended, Kishore sir.
Sir, no. Yes, sir, sir. So that was a wonderful session, sir. So
Yes,
today,
yes.
so by this session, so we are going to end, sir. So tomorrow we have 3 sessions, sir. So
Okay.
as per the schedule given from the AICTE, so sir,
Uh-huh.
actually, I'm contacting the resource persons again, sir, depending upon their availability. So session will start from 2 p.m., sir. So
Okay.
2 to 3 or 3:30, like that, 3 sessions, sir. After 3 sessions, so you will have test, sir, assessment test. So it is going to be like with the help of Google form only. We will share the Google form link. So
Okay.
questions maybe like 30 to 40 questions we are planning, sir. So we'll
Okay.
give some time limit for it.
Okay.
After that, we'll have valedictory, sir.
Okay, sir. Actually, sir, I am waiting to attend the session that is related to the machine learning, network optimization.
Sir. So actually, what is happening, sir? So when the speakers gave approval,
Huh.
so they said the date and topic okay, but after that, what happens? So due to their busy schedules, some were unable to deliver the same topic, or some were could not able to deliver because two resource persons actually they are moving from their institute to some other institute. Okay, so we could not force them to exactly deliver the topic or exactly deliver on that. That's why the timetable is changing, sir. Please kindly understand, sir.
Okay, because I am working on the network optimization with the help of machine learning and these
Sir,
things.
sir,
So I'm trying to find out any
sir,
research
sir.
related.
Sorry, sir. Tomorrow we will.
Okay, anyway.
So participants, please tomorrow join by 2 p.m. So again, if there is
Yes,
going to be any
yes.
change, I'll update you in the group. So after filling the Google form, and you need to submit the feedback from your portal, from your login. So that is mandatory. And tomorrow again, I'll give you the guidelines. So depending upon the resource person availability, so if there is going to be any change, I'll post it in the group. And regarding PPTs, every time, that means every day, I am asking the resource persons. So two PPTs till now I received. So those I'll share it now. And regarding today morning PPT, sir, what sir is saying, sir was saying I need to take the permission from my DL team. So that's why. So there are some constraints for them to share the PPT. And coming to the NIT, Kishore Kumar sir and Anjanel sir, so they are also hesitating. Actually, they are shared their work, what they are going to do. So maybe in a couple of days we will expect. So kindly cooperate with this. So once I received, immediately I'll share it with you. And anyway, we are going to share the YouTube link. So please spare some time to watch those videos, so you will get everything. Okay, anything to be discussed, we'll discuss, or else we'll wind it up the session. Sir, it will be better to keep the exam in the evening. Yes, sir. If exam we are going to keep it in the evening only, sir. After 4 or 5 p.m. only, sir. Because after once all the sessions over, then only we are planning to conduct the exam, sir. After 4 or 5 p.m. only. Once those 3 sessions done, then only we will share the link for the Google form for exams. Sir, anyone want to ask anything, or shall we wind it up?
Thank you, sir.
Okay, sir. Thank you, sir. So, dear participants, okay, sir. Somewhere six. Okay, sir. No issue. So, we are not going to restrict the test for certain time limit. We will give some time for you. So, if you are having some work during that time, you can write it after that work. So, no issue, sir. So, we are not going to put certain time limit for the exam. We'll give some time, sir, for it. Sir, kindly try to join tomorrow session, sir, because you are seeing some of our not attending the session regularly. So up to some extent I can do, sir, but What AICTE asking some regardings also. So in that I cannot do any manipulations. So kindly at least try to join tomorrow's sessions completely, sir. Okay. So thank you everyone. So Sir Karthik sir will share the Google Form attendance link in the group. So please fill it. So thank you everyone. Karthik sir, you can leave, end the meeting, sir.